Okay, good evening. Let's resume this. Uh, so review is what I've been trying to do here. So slowly going over the topics and then maybe spend more time on issues that are less, that have received less attention. And, in retrospect, some issues will look different, I hope. Um, so some of them should become much easier for a simple reason that we have seen them so many times, or maybe not. So it's really hard to tell until the final. Um, okay, so once again, we're gonna have those presentations next week. So we'll make up a schedule tomorrow. Okay, so probably we should have the first 3 days, so not Thursday, I guess. Maybe Thursday too. We'll see. So we have 5, but no more than 15 minutes each, or maybe 20. Yeah, we should be all right. Okay. So once again, if you have any topics you want that you think need special attention, just let me know. Okay. Yeah.
The projects that we're turning into you are due tomorrow, and the
Right.
presentations next week.
That's right.
Okay.
Yeah. So don't forget that. So it's the format is just printed out, so I can just start reading it, and then the digital format by email. If you have any kind of Excel spreadsheet that you should explain as much as possible everything in the text. That is the one that will be evaluated, and then but if you have something to send, then because you cannot attach Excel to a piece of paper, so if you want to do that, just email it to me with the digital submission. But we'll still have time to talk about it next week during your presentations, and you'll certainly have time to present. So we'll talk more about that tomorrow. In the meantime, so we are early in the so it's like what is it? Early September or something like that. So the limits, the continuity and continuity, the limits of sequences, functions, and continuity of functions. Okay, so this is a very central part of that topic. It's applicable to both functions. The substitution rule is applicable to both functions and sequences, and it will come up also next semester, presumably. So you're taking Calculus 2. Okay, so I do try to not overemphasize anything that would not come up just about a lot in Calculus 2. And I think just about everything will come up in Calculus 2, and Calculus 3 is kind of the same thing, only in a multidimensional environment. Okay, so Calculus 2, especially sequences, will appear in the form of series. So it's iterative or incremental or recursive introduction of computing or definition of sequences. And that's what we're going to be dealing with, a large part and the most challenging part. So if you understand sequences now you will be much more comfortable next semester, which is by all accounts, that part is the most challenging. Why? Because not frequently, but just about every time sequences do not appear in Calculus 1. So I try to remedy that at least a little bit, so we can. We have some leg up here, and then so that one large topic, and that's the challenge of Calculus 2, is the 3 major, hardly overlapping topics: series, integration, which we only touched upon, and so all the big applications, as well as techniques of integration will appear. That's the second, and the third one is introduction into multidimensional calculus, that is parametric curves. So that's the challenge, the challenge of Calculus 2. So hopefully we'll be well prepared. Okay, so that's a substitution rule. So once again, every time in doubt why something works so well, it is the continuity of of the function is the reason for it. Naturally, whenever the derivative is involved, then the presumption is that the function is differentiable. So we'll get to that shortly, but the continuity, with the continuity comes the question that just did not come up. In a way, the opposite came up, is what functions are not continuous. So the presumption is over here, that's a very convenient way of looking at things, that functions typically are continuous on their domain. So if there is some division by zero here somewhere, or square root, you find the domain, then every point within the domain, the function will be continuous. Okay, so once again, 1OX, there you go. So this is the domain, hole in the middle. So wherever, if you step away from zero, then at every location of the function, it will be continuous. And then the gap appears at the same exact spot where there's a gap in the domain. Okay, so we don't have a problem with that. On the other hand, there's also one-sided continuity in functions such as square root, which is this one looks a little bit like a square root, and so that's why I'm using it. It has an end point in the graph. Okay, so then you should know what one-sided continuity means, because technically we are supposed to look at x's from left and from the right approaching that value. So I'm not going to spend too much time with that. It is really just something to be familiar with the issue rather than try to remember the whole thing. So like I said, one-sided limits, one-sided continuity. But other than that, if you pick any point over here, it is perfectly all right point, and the function is continuous. To the left of zero, there is nothing there to worry about. So then the issue becomes, remember what I point out, I tried to make yesterday, is that examples are so important that for every issue or every definition, concept, theorem, formula, there might be a few examples, overlapping examples of functions or sequences that illustrate them. Okay, so like I said, 1OX illustrates the fact that functions are continuous on their domains, and there's a gap, missing point in the domain. On the other hand, the square root function illustrates the idea of one-sided continuity as well as one-sided limits. Now, what function illustrates this continuity? So what is the simplest? Naturally, when you want to illustrate something, you pick the simplest example. What's the simplest function that is discontinuous? But once again, 1OX is discontinuous, but only if you count the point where it is undefined to begin with. So it's not really a good example. So what's the simplest example? Not necessarily simplest, but the most important example. Remember this one? Does it ring a bell?
Is it a constant function?
It is what?
Multiplied by a constant?
It is constant. It is, see, there are only three values, and it is constant to the left of 0 and to the right of 0 separately. Okay, and you certainly can see the discontinuity because of the gap. That's number one clue that there is a gap between the values, indicate the discontinuity. So that the picture certainly number one for you to remember what discontinuity typically at its simplest looks like. It's a gap. Okay, so there are other types of discontinuity, but this is the most typical and the good enough to illustrate just about anything about discontinuity, non-existing limits, and stuff like that. But then, so in addition to this picture, you also need to remember the formula. So remember the formula, or can you reconstruct it? Maybe. So this is -1, this is 1. So how do we deal with functions that look like this? Well, you might try to look at them separately. So what should I write here? F of x equal 1 for all x larger than 0. Here, f of x equal -1 for x less than 0. Over here, f of 0 is 0. Okay, so 0. So that's almost the whole definition. But the familiarity with the concept, what's the concept I'm talking about here? What do we call these functions? As you can see, there are 3 formulas, pretty much. We make it of pieces, and that's why it's called piecewise defined function. So those are not parabolas, hyperbolas, not quadratic, cubic, not trigonometric, but rather they are made of pieces, and those pieces could be any kind of function. So piecewise defined. And they are typically used to functions like that build up in order to most of the time illustrate discontinuity, or continuity or discontinuity, as well as differentiability and non-differentiability. Okay, so we'll get to the latter shortly, but at this time this is supposed to illustrate the simplest function, I suppose, that is discontinuous. Okay, so then the piecewise defined, this is how we write them. So another thing that you need to remember, so -1 if x is less than 0, 0 if x is equal to 0, and 1 if x is larger than 0. Okay, so that is a piecewise. 3 pieces. The domain is everything, and it's split into 3 pieces, and then you have 3 formulas. They might be as simple as this. By choice, it is the simplest, but they could have any kind of formulas. Okay, so that is the function. So another function that you keep in mind at all times, or not at all times, but at least at your fingertips, so that you can pull it out to illustrate whatever the concept we're dealing with. And we are right now we're actually looking at the substitution rule, which rely on the fact that the function is continuous, and so now we know this one is not. So then suppose I take that expression over there and replace my sine function with this sine. Oh, I'm doing this again. The sine function I'm going to replace it with the sine function. So that's a joke. So this is the sine function. Okay, so sine and sine functions, and and then as you can see, they're different. So if I try to write limit x goes to 0, sine SIGN x squared, then the trouble is that trying to do exactly the same thing, it only differs in 2 letters, right? SIN or SIGN. That's the only difference, an extra g. So it is tempting to do the exact same thing, and I write SIGN, limit x squared, okay, and x goes to 0, and then I continue in the same manner, and I have what? I have 0 sine of 0 is equal to 0. Okay, so you see a problem here. So what's the problem?
X can't be less than 0.
No, it could be. No, there's no problem there. No, I have sine of the limit. Inside the parentheses, all I have is the limit of x squared, x goes to 0, then x squared also goes to 0, so there is no trouble with this one. And then I end up with sine of 0, and look at it. Sine of 0 is 0, so the answer is 0. But the problem is elsewhere. Where's the problem? At the question mark. The magic words. What? I'm using the substitution rule, okay? However, the substitution rule the rules are to be used when the rule might be a slightly misleading term. It is more of a shortcut, and there are prerequisites for taking a shortcut. So if you were driving. There you can cut through the woods. You got to check out that your car or truck can handle a road, off-road driving. Okay, so if you do, you check it, you take a shortcut. Okay, if you without checking the prerequisites, preconditions of these shortcuts, then you're in trouble. So that's exactly what has happened here. So it's not just a question mark, but it is really that's a mistake, because you cannot justify the transition. So you cannot justify transition. You cannot justify the substitution rule. Then you cannot use it. Okay. So then the only way would be, well, then you see what happens is what to do is next question. The first one, what not to do, and this is what not to do. So because you're justifying with the same exact words, and if I try to justify it because SAGN is continuous at x equals 0, but the graph of sine is right here. It is not continuous, as we just discovered, at 0. So no. So the substitution rule does not apply. Just as we've seen elsewhere, you take the quotient rule, and then end up dividing by 0, and you have indeterminate expressions. So it's the same story. So you realize that something is wrong, and if here it is very pernicious, if you like, because the mistake is hidden, because when you do it division by 0, you'll know that you're in trouble at the end. Here, look at it. If you use the substitution rule, you will, at the end you have a 0, and unless you have another reason to know that the answer is wrong, you won't discover that it is. Okay, so that's why you cannot see a stop sign or end of the road sign and go back and redo it. No, everything will be fine. You will just arrive at the wrong destination, and you will never know. Okay, so that's why I always verify the conditions. Once you realize that this is not applicable, then what do? You discard this part, because that was wrong anyway, and then you figure out what to do, and then now that the big lesson is that what not to do. But still, if we want to answer the question as it is posed, what's the answer? What? Yes, the answer is 1, as a matter of fact, yes. The answer is 1, that's right. So if but there's the answer because because of the x squared. X squared is what makes it possible. If I put it sine x, well, how about x cubed here? What's the answer for this one? Well, you need one answer. When you have two answers, what does it tell you? Does not exist, right? So as you can see, sometimes you don't know. In either case, the first example, the second example, the trouble you run into is the same. If you try to apply substitution rule, it is not applicable because the function is discontinuous. But then the result could be anything. It could be 1, could be -1, or it could be the limit still might not exist. So it's unpredictable. So it's just like I said, the wrong route may take you somewhere place, and you won't even know you're in the wrong place. Okay. So that is the continuity really goes through the rest of calculus and beyond, and so does does composition. So which is what we're looking at here. As you can see, sine and x squared. The substitution rule is about compositions. Okay, so both of these topics go through calculus and beyond. So another related topic I want to review, so it's not technically calculus, and that is the inverses. So first of all, you got to know the concept, and you got to know the examples. So which one is the more important? It's hard to tell because at this time you already everything is a kind of a
Melting pot.
what?
Melting pot of knowledge.
Right, yeah. Hopefully it makes more sense. So, but the order has disappeared. So we did it in a particular order, and so if that's how you learn. But then at some point, it's like food. It's just hopefully it is being digested well, and it is mathematics, it's science. So parts of it interact with each other and they support each other, and the new things that you see you might be able to find a place to fit it in, and it would make sense quicker than if we were just starting. So inverses. Concept needs to be known, but also examples come in very handy to just to make sure that you understand it, as well as if you forgot it, you don't remember the concept exactly. Maybe you don't remember the definition. A lot of people forget the definition of inverses, but if you get the idea, at least you won't make big mistakes, or only just small ones. So how do you understand inverses?
They're basically the opposite of something.
The inverses. So inverses is a kind of a term a little bit misleading unless you think of it as correctly. Inverses. Why is it plural? Because the inverses come in pairs. So function and its inverse paired up. So you go from function to its inverse, or you go backwards, and it will be inverse. The inverse of the function itself. Okay, so that's the main thing about it. And they are inverse in what sense? So they are opposite. But as long as you don't, you just don't replace the word inverse with the word opposite, and just as well you can replace the word opposite with the word inverse. So there is some mathematical concept that underlines this idea. What is it? What we just talked about. In what way are they opposite?
Variables are swapped around.
Okay, that's it is not the whole story, but that's an important part of it. So if you have y equal x squared, then you have possibly x equals square root of y. These are the two inverse functions of each other, and it's not that the variables they are swapped. The dependent variable becomes independent and vice versa. Okay, so it's not the whole story, but it is very important to remember. And if that's where you start, you might be able to connect the dots. Okay, so that's roughly what you see. That would be a pretty good example to start with if you're thinking about inverses. So it is a pair to begin with. You also know how you can get from the first to the second, or from the second you can get the first, right? So simply solving the equation. Okay, the other issue that you will discover here So once again, you solve it either from left to right or from right to left. Solve for x, solve for y, and you go back and forth. Okay, so it's a pair. Another issue is certainly if you plot it, you can say, well, I plot x squared, right? And then this is a graph of a function on the left. Where's the graph of the function on the right? It's the same thing, except all we do is just put x-axis vertical, and you have the same exact graph. There's literally no change of the graph. So this is what I'm talking about. It's the same graph because the relation between x and y is the same. It's just we just decide which one comes first, which one second. That's all. So that's how you, from one good example, you can recover all the concepts about all the ideas or even problems and pitfalls about a concept. So the pitfall here is that is there here. What am I talking about here?
Flip across the y-axis.
No, you see, this is the y equal x squared. It does not have one branch. It is a parabola. It has two branches. So what happened to the other one?
It becomes undefined.
Not undefined. If I flip this function, what happen? If I flip the original function with the whole parabola, I'm getting the other graph. What's wrong with that graph? If I add this part, why is this a problem?
Because if you do the algebra, you can't get a negative number.
That's right. So that's right. The problem is if you want to think about it algebraically, indeed that what I have over here, solving the problem, it only works out whenever x is positive. Otherwise you're not going to get a formula for the second function because there are two, and that gives me the second interpretation of this problem, and that is the new function. The new function is not a function. Right. So if I include negative x's, so that's the problem here. If I include negative x's, I will have two answers for the same question, negative and positive, and then the only way to resolve it, I would have x equal plus or minus y, and that's simply not a function. Okay, not a function. If we include this part to the domain, so we had to cut it. So once you realize that that's what has happened here, there is a terminology that you need to remember in order to describe it. So what is the difference between this function on one hand, so this is good, and there's a name for functions like that, and this one, it is bad. In what sense is it bad? It's parabola. There is nothing wrong with it. Well, why is it good? This is bad. Right, so its inverse that we thought we had does not pass the vertical line test. That's on the right over there. But if we go backwards and look at the original problem, original graph, then this is what we're facing. It's not a horizontal, not a vertical line test. It's a horizontal line test, right? So the first function that passes the horizontal line test, both of them are functions. You don't want to, the idea here is you don't want to go and try to find the inverse and then discover that the new function is not a function. Okay, so instead, you dealing with the vertical line test of the new function, you just apply the horizontal line test to the original function. It's pretty much the same thing. And you can see the difference between bad and good and bad, but there is as in mathematics, you have to know the terms. So the good one, what is it called? Well, the terminology is important, but the concept, knowing the concepts is more important, but that term is, sometimes terms are descriptive, and they actually help you to remember things. Sometimes they're not, but this one is, and the problem with the second function, you can see that there is a, well, we already discovered that for one value of y, there are two values of x. But that's not the case with the first one. For each x, there's only one y, and for each y, there's only one x. That's what we see on the left. That's the good thing. And so, does it ring a bell? What term I'm trying to?
The function is 1-to-1.
1-to-1. So this is 1-to-1. So once again, 1, 2. 2 refers to the function. So this is f, this is x, and this is y. Okay, so for each x under f, there's only one y, and vice versa. For each y, there's only one x. So these are the inverse functions. These pictures are descriptive, but then specificity kicks in, and the requirements sometimes are specific functions that you're facing. So you got to remember those pairs of functions. So this is one. The inverse of x squared is square root of x cubed is cubic root, right? Whereas sine inverse is, well, let me put y here. Inverse of sine is arcsine. So there is really no special, there is actually special notation for it, but if you write it this way, it is just as good. So it's called, the word is arcsine. Arc sine. I can't remember why it's called this way. Trig function, so arcsine, same problem. Sine is not 1-to-1, so we have to cut piece of it in order to make it 1-to-1, and then there is an inverse. Okay, so so that's what sine looks like that. And so if you allow it to tip left or right or go down, then it's not 1-to-1 anymore. So you have to limit yourself to this, between negative pi over 2 and pi over 2. And then it is 1-to-1. Okay, cosine similar. The one that is frequently forgotten is the exponential function. What's its inverse?
Log y.
What?
Is it log y?
Log y, base e, natural log. Okay, so these are the main ones. These are the main ones. The rest are found. So these are to be remembered. The rest are found by the way we did it over here, by solving for x. So y equals x squared. So for x, you find the inverse. As you do that, you will discover whether or not the function is 1-to-1 or not. So when you're solving it, y equals x squared, you take square root, then you need to know that the plus or minus appears. So every time there's some square root you're trying to take, you know the plus or minus will appear. So, and that means that the function is not 1-to-1 unless you limit its domain. Okay, the main thing is if f is continuous, then so is f inverse. That certainly is the main fact to be remembered. But then this is what you would expect to have. It's a relation between x and y, or is it between y and x? So there is no gap or break or hole in the graph of the function. So you just all you did it over there at the top on the right. We took a piece of paper with a graph on it and we flipped it. Okay, so certainly there is no way there's some kind of a break has appeared on the graph. So okay, so that is predictable. Well, I'm still back to the concept that underlines the whole thing, which is kind of not obvious, but that concept is broader and more important, and that concept is the composition. So we're back to compositions again. The concept underlying the idea of inverses is the composition, because, and we had the whole discussion without it, but if you want to really understand it, it is the composition. The two functions composed with each other will cancel each other. Okay, so x squared square root is equal to x. That's the cancellation. So you like take these, and they are canceling each other. Okay, so that is a composition. Another one, e ln x, once again is equal to xy, because this part is canceled. So so it's all about compositions. Okay. Okay, so we have all kinds of nasty examples of poorly behaved functions, and I think I'll bring this one again. A poorly behaved function, which is continuity of kind of one of the worst, discontinuity rather, discontinuity of the worst kind. Well, there's always something worse than that, but this example of something that is certainly qualifies as one of the worst kinds, and that is, you remember this one, function that oscillates faster and faster and faster and never stops. Okay, so that is really nasty behavior. You don't even see gap. Where is the gap? So if we're used to the idea that discontinuity is a gap, well, not always. It is, in fact, more stuff going on, more graph than you'd think. So the gap, well, that's discontinuous. We know that. And this is, it seems that there is no gap. But the oscillation is just never slows down, and so there is no literal gap, but there is this jumping up and down, and so the point is that the function remains even undefined and here, but the point is that there is no way we can add any value to it in order to make it continue. So I'm not going to go deep into that, but just remember the function sine 1 of x. Okay, so x goes to 0. 1x goes to infinity, and as the argument, the variable of sine goes to infinity, sine oscillates, and that you end up with this. Okay. Okay, continuous function is bounded on a closed interval. On a closed bounded interval. Okay, so that's a theorem. And furthermore, reaches its maximum minimum values. So these are concepts that are very, how should I say, uncomputational. So when you're computing derivatives or integrals or something like that, that many problems of various kinds that calculus is good for, this might not come up. But it just fills the blanks. Well, the last one especially is important. You can certainly see how the first one connected to the second. So if the function is not bounded, then it never reaches its maximum because the maximum is infinite. Okay, same with the minimum. So that's the starting point. And why do we care about the second? Why do we care that a function reaches its maximum minimum values?
Because that's the range.
It is the range. So the range will be then the range will be an interval, and as a matter of fact. So if the function is defined on a closed bounded interval, which is AB, okay, then its range also will be an interval. But more specifically, what I'm talking about is that this is maximum minimum. So we, if we're trying to solve an optimization problem, we'd better make sure that if we know that the function is continuous, then we know that there is an answer somewhere. Okay, so we're starting the point, the problem, solving the problem, knowing that the answer is there. You just is to be found. So it applies to optimization. So if the function is not continuous, or it is just then it may be going to infinity, or maybe it oscillates like that, and then we're also in trouble. Okay. Intermediate value theorem. Okay, I'll skip it. So this is a very abbreviated way of thinking about continuous functions in this respect. If you just think about its range. So a range of a continuous function defined on an interval AB is interval CD, roughly. Okay, interval including the endpoints. So in that sense it behaves very nicely. Okay, so the next topic is asymptotes, a variety of, so vertical and horizontal for the most part. So any issues with that? As always, going back and forth. So you might have a function given by with a formula you need to discover its asymptotes, or vice versa, you have a picture of a graph and you need to describe it with appropriately. So you say that this is an asymptote. If you see it, you say it's an asymptote. But furthermore, there's asymptotes that are described appropriately with limits because that's what they are. So if you see something like this, so say 3, and you're looking at the graph looking like this, y equal f of x. So that's all you see. Okay, this is the whole picture that's given to you, and you're supposed to describe it well, just describe it. You see that's the thing about it. When you see it, you don't want to make up words to try to describe it. The language is already there, and now it's your task to convey that information using that language to somebody else. So you don't want to describe it starting from scratch. But rather just you remember, that. So how do I so what's the answer? How do I describe this?
With an asymptote of y equals 3.
Y is 3 is
Asymptote?
a horizontal asymptote. Well, I mean it is presumed y equals 3 is horizontal, but still, I think it's better if you say it's horizontal. And then slightly more advanced way to describe it with a limit. So, how do you describe it? Well, it's always x versus y. So once you make the first step, you know what's going on. All you have to do is just to express it in terms of a limit. So this is what we're talking about. So what's happening to x, what's happening to y, and you just write it down. X approaching what? Right, technically plus infinity. So as x approaches infinity, y approaching 3. Alternatively is you would write it, say, f of x approaching 3 as x approaches plus infinity. So it's just another way to put it. So whether I like this one better. In fact, it's the most revealing. It just tells you what the picture says. That's it. And the next one, it refers to a function. So it's slightly better, I suppose. And then yet one more. It is if you want to use LIM notation. So LIM, x goes to plus infinity, f of x is equal to 3. That's the last one. Okay, so several ways to do it. So the last 3 are all equally good. Okay, and then you have the same with the vertical asymptotes. And as I put plus there in order to emphasize the point that sometimes the asymptote might be on one side but not on the other side. So a few examples of functions then in order of that illustrate the idea of asymptotes. The most standard one is y equal 1 of x. Okay, so it has both vertical and horizontal asymptotes. So you start thinking about asymptotes, 1 of x should be your go-to example. So you see what it looks like. You can also recover all the algebra. You can recover all those definitions over there, limits, and so on. So x goes to infinity. Where does 1 of x go? Well, of course it goes to 0. Okay. So or if x goes to 0, where does 1 of x go? Well, it goes to infinity. So it's one example pretty much contains everything that could possibly happen. But you still, if you still need more, example would be e to the x, which has asymptote on one side and no asymptote on the other. Okay, so that's one-sided. So besides these, remember more functions with vertical asymptotes or horizontal asymptotes in addition to these.
Y equals x squared has a horizontal asymptote at 0.
Y equal x squared? No.
Doesn't go below the...
No, this is a parabola. Parabola does not have asymptotes, no. So you see asymptotes are either vertical or horizontal. In either case, the graph is approaching that straight line, and but by that it is flattening into a straight line, either vertical or horizontal. There are also oblique asymptotes, but we don't worry about that. So that is also actually, as a matter of fact, a good example of a related issue. What functions do not have asymptotes, and most of them don't. No polynomials have asymptotes. They first of all, they do not behave like this to begin with, because they go to infinity, either one or the other. And then vertical asymptotes, also there are no vertical asymptotes. They're defined at every point. So polynomials are good that way. But rational functions such as 1 over x have asymptotes of both kinds. Well, not each of them. Some of them have vertical but not horizontal, and vice versa. The function that I was thinking about is the tangent. The tangent has vertical asymptotes. Okay, so we'll stop here. So bring the projects tomorrow.